The following program is brought to you by Caltech.
Good evening. I'm Michael Werner, the Chief Scientist for Astronomy and Physics at JPL. It is my privilege to introduce tonight's Watson Lecturer, my good friend and colleague, Jamie Bach. Jamie's talk will present scientific highlights from the currently operating NASA European Space Agency Herschel Space Observatory. Herschel, like several space observatories which preceded it, studies the heaven in the infrared part of the spectrum. Jamie will be placing Herschel in its scientific context. I wish only to point out that over the past few decades, we have come to realize that observations and studies across the entire electromagnetic spectrum, from the gamma ray to the radio, are required to unravel the mysteries of the astronomical universe. As Jamie will show, infrared studies provide critical pieces of this puzzle, and I am pleased to note that between JPL and Caltech, Pasadena has been instrumental in most of the nation's most powerful infrared space observatories, including IRAS, Spitzer, Herschel, and the recently completed WISE All-Sky Survey. Jamie graduated from Duke University in 1987 with all kinds of honors and went on to Berkeley, where he became one of Andrew Lang's first graduate students. Even before Andrew joined the Caltech faculty in 1994, he arranged with Charles Elachi a postdoctoral appointment for Jamie at JPL. Jamie has thrived at JPL, where he has been able to combine his technical genius and his scientific insight into detectors and instruments which have revolutionized long-wavelength astronomy and are currently in use throughout the world, and, as you will hear, in outer space as well. He has received numerous awards, including designation as a Presidential Young Investigator, JPL's Lou Allen Award, appointment both as a Senior Research Scientist at JPL and as a Senior Faculty Associate at Caltech, and NASA's Exceptional Technology Achievement Medal, awarded for the work he will describe tonight. Please join me in welcoming Jamie Bach, who will present this evening's Watson Lecture, Revealing the Cold Universe.
Thank you, Mike, for that kind introduction, and welcome everybody. My talk tonight is on the Herschel Space Observatory and how Herschel, with its far infrared vision, is unveiling a hidden cold universe. But that's just part of my story. The other part of my story is the hidden tale of the specialized detectors in Herschel, their modest beginnings, and the unique environment at JPL and Caltech that made them possible. Now, when I was putting this talk together, I thought back to how I initially got interested in doing experimental astronomy. And it really started when I was a graduate student. I did my thesis project on a sounding rocket experiment in Japan. And the project before my project, which was another sounding rocket experiment, was a pioneering, technically ambitious cosmology experiment. And in many ways, this experiment was a strange convergence, a technical precursor to Herschel. It had all the same technologies. It had bolometers, a low-temperature cooling system, the filters and electronics. And it wasn't just the hardware, it was actually the people, the groups involved in making this sounding rocket experiment went on to collaborate for several decades, and we're still collaborating today. And were major players in one of the instruments on Herschel. And so I was thinking, what did I learn from this experience? And I really learned two things. The first thing I learned is that this was a small experiment, and the idea that a few graduate students could build something with their hands that would make a fundamental measurement about the early universe, that idea was very seductive, and it really changed my life and how I did science. The second lesson followed shortly on the heels of the first lesson, And that was that we really weren't ready. These technologies were in their infancy or maybe in their ornery teenage years. And so we really struggled, but we also learned a lot very quickly. And so technology is important in astronomy, and I've spent a lot of my career working on technical problems. And one of the great things about JPL and Caltech is when you have a new idea or a new technology, you can go out and immediately use it in a science experiment, and you learn a lot that way, and as well as you have a lot of fun. Okay, so on to Herschel. The Herschel Space Observatory is named for William Herschel, and William Herschel was a musician and a composer. That was his day job. But one of his passions was astronomy. Shared with his sister, Carolyn, and also later his son. William Herschel was very much a hands-on guy. He built his own telescopes in the basement of his house. And when he discovered Uranus, he became a favorite of the king, and he was appointed the king's astronomer, which he liked to remark resulted in a cut in pay. This picture here shows how Herschel discovered infrared radiation, and that hands-on approach, I think, paid off. What he's done here is he's got an apparatus that's kind of looks like that mailbox thing, which are some optics that are shining sunlight through a prism onto his desk. And he has a few thermometers there, and by placing the bulb of that thermometer at different places in the rainbow, he can measure the heat produced by sunlight. And his key insight was to take one of those thermometers and put it out beyond the visible spectrum, out beyond the red. And what he found is that the thermometer continued to heat up, and so there was some unseen radiation out there beyond the red that was causing that effect. Okay, now what does Herschel, and I mean Herschel the spacecraft now, what wavelengths is Herschel sensitive to? Herschel's a far infrared submillimeter telescope. And so it's sensitive to radiation here that's about 1/10 of a millimeter and spans a range from 60 microns on the short end out to 700 microns on the long end. What I'm showing here is a plot of a spectrum of a common object. This is the spectrum of the sun. It tells you how much energy is coming out from the sun at every wavelength. With our eyes out here in the visible, we're very well attuned to the peak of this solar spectrum. Now, if I take a cooler object, a candle, this spectrum shifts out to longer wavelengths, and by your eye, you can see a candle, of course, is noticeably redder than the sun. Now, if I take a person, and you may think of people having a temperature of 98.6 Fahrenheit, and I've plotting the temperatures of these various objects in absolute temperature units above absolute zero. So in Kelvin, a person has a temperature of about 310 degrees Kelvin. A person is not visible, obviously, in the optical, but they are quite luminous out here in the mid-infrared. And you can see the general trend is colder objects emit out at longer wavelengths. Well, what's the coldest object that we have daily experience with? I guess that's the freezer in your kitchen. And an interesting thing happens here. The coldest thing we have daily experience with the freezers, on this scale is not really that different from the temperature of a person. Our senses we're used to a narrow temperature range, and our sense of temperature of cold seems to saturate around this temperature, and everything else just feels really cold. Dry ice, like if you're packing a lobster from Maine to ship out to California, you can see it is colder than your kitchen freezer, but not by a heck of a lot. Okay, so what Herschel's sensitive to is the interstellar dust and material that lies between the stars in our galaxy and other galaxies. And that material often has a low temperature. And in particular, it's not uncommon for interstellar dust, this material between the stars, to have a characteristic temperature of 20 Kelvin. And these temperatures are perfectly suited for Herschel, and so these are the sorts of things we see with Herschel. Now, when I say interstellar dust, this brings to mind a certain image. And of course, I don't mean the dust that's in your house. What do we learn by studying interstellar dust? Why should we care? Why is it important? Okay, this is a classic picture of the importance of the infrared. What I'm showing here are a pair of interacting galaxies. They're called the antenna galaxies. And while this is kind of a classic example, when I was researching this talk, I found that they were discovered by William Herschel. So I kind of had to talk about them. They're called the antenna because there's this two long trails of stars from these two galaxies that look like the antenna of an insect. But you can see the two nuclei of these galaxies here and here, and this is a very nice optical picture provided by the Hubble Space Telescope. And then there's this kind of messy region in here between the galaxies and this kind of dark, opaque stuff. What the heck is going on there? Okay, now if I switch here, we can see what these galaxies look like in the infrared. And the infrared gives you a different picture. That messy region between the two galaxies is where the infrared is really the brightest. I mean, you see the two nuclei here, but all this stuff is very bright in the infrared. So what's going on? Now, if you go back and look at the optical picture, you can see all these red regions. And this is ionized gas that's coming from young stars that are born in these clouds of interstellar gas and dust. And star formation is kind of a messy process. Stars are born out of this material, and as they turn on, they're in these dense, shrouded environments. So what happens is it's easier to see this emission out at longer wavelengths in the infrared. So I have a little demo that describes how this works. Okay, this is an infrared camera. It's actually bolometers. It's sensitive out in the mid-infrared. These are room temperature bolometers, and as I mentioned, people are very luminous out here in the mid-infrared. You can see the heat from my hand. And I have here a star. You have to wait for the star to warm up. There you go. All right. And this is interstellar dust. It's a garbage bag. And you can see this interstellar dust is not very transparent in the optical, but in the infrared, you can see through it. It's somewhat transparent. And if I double up the amount of interstellar dust, it gets less transparent. Still kind of look through it. I can take this to an extreme case. Here's some serious opacity. This is a metal box. You cannot see through this. I guarantee it. And if I put this over the star and walk away and have a little bit of patience, what you see is the whole box starts to glow here in the infrared. In fact, if I had a calibrated camera, I could measure the brightness and the temperature. I would know how much power is coming out of this box. And I could infer that there was a 40-watt something inside the box that was generating that energy. And so that's basically the idea. In the far infrared, we can actually see the material here glowing, heated up by stars. But it's even better than that. With Herschel, we don't really need a star. The wavelengths and sensitivity of Herschel allow us, wait for the star to go off here, but it allows us to see interstellar material that's in ambient conditions. Don't have to have an embedded star. And so with a little heating just from diffuse starlight, we actually just see the interstellar dust itself. There you are. Okay. So if I go back to this galaxy, now this is a local galaxy, and as I said, the infrared is important for this galaxy, but we can ask the question, how important is interstellar dust in the process of forming galaxies, distant galaxies, the galaxies way back in the distant past of the universe? And we actually have a pretty good idea about the answer to that question, and that's because the sky isn't perfectly dark. And I don't mean the sky in Los Angeles, I mean that the light coming from outside of our galaxy isn't zero. It's produced by the integrated emission of galaxies between us and the Big Bang. That whole history of galaxy formation comes out as a diffuse light. And we can ask the question is, how bright is the universe at every wavelength? And the answer is a bit surprising. It turns out that of the light produced by galaxies, about half of it comes out in the optical, which is not too surprising because you see stars, but also about half of it comes out in the far infrared. So if we want to understand the history of our universe and understand how galaxies are formed, we're missing half the story if we just study them in the optical. We really need to go into the far infrared to get the whole picture. Okay, now I mentioned interstellar dust, but most of the material between the stars is really in the form of gas. And most of that gas is hydrogen and helium. But once again, here the infrared and Herschel can tell us a lot. So this picture here is a cartoon of the process of star formation. Stars form out of this interstellar material. And how does that happen? Well, one thing is that the importance of metals in this process, and by metals, I mean metals in the astronomer sense, which means anything that isn't hydrogen or helium. These metals can radiate away the heat of this gas so that very diffuse gas is able to collapse down into denser regions where star formation can happen. And metals like carbon, nitrogen, and oxygen radiate away this energy in the far infrared. As this process goes further, as you get to denser material, molecules start to control the cooling process that leads to star formation. And molecules like carbon monoxide are very important, as well as water. And water is a really interesting molecule. It's very hard to study from the Earth because our atmosphere has water in it, which blocks our view. But from space, we can study water, and the role of water is a big science driver for Herschel. And so what Herschel's telling us here is really not how stars are born, but what happens before stars are born. How does this material enable the formation of stars? This chemical series gets more and more complicated. It eventually turns into chemistry and organic molecules like methanol and ammonia, and something called a polycyclic aromatic hydrocarbon, which is basically an organic chain. These are molecules that kind of mimic interstellar dust, but they're very small molecules, kind of like the molecules that come out of auto exhaust or your charcoal grill. And the interstellar chemistry is actually very, very, very rich. Okay, how can we detect infrared, far infrared radiation? So the classic detector for doing this is something called a bolometer. It's a very simple detector. It consists of an absorber which takes infrared radiation and turns it into heat. In fact, it doesn't have to be infrared radiation. It could be any radiation. It could be X-rays, and people use these for detecting X-rays. So you take that radiation, you turn it into heat. This absorber is weakly coupled to a thermal bath, and so that absorbed energy heats up the absorber, and you measure the temperature with a sensitive thermometer. This is the earliest example that I know of a low temperature bolometer used as a detector. This example is a little bit ahead of its time. It's got a really nifty idea. It's using a superconductor as a thermometer. Superconductor is a very good thermometer. And it has a really nifty cooling system here. And here's Dr. Anders waving his hands around, and you can see him in this scope, kind of. In spite of the marketing panache behind this, it didn't actually really catch on very well in astronomy. That changed in 1961, and when Frank Lowe invented a thermometer with a different thermometer, bolometer with a different thermometer made out of germanium. And astronomy, infrared astronomy, really started to take off in the 60s, and Caltech was at the forefront right from the beginning. There's a group at Caltech led by Gary Neugebauer that built an infrared observatory on the summit of Mount Wilson. You'll notice its accommodations are a bit more modest than that of an optical telescope. They used a telescope that was designed by Bob Layton, who was famous for the Feynman-Layton Sands physics lectures. And this guy here is Jerry Nelson, who went on to build the Keck telescopes. From these early days, in about 20 years, came the first infrared satellite called IRAS. And IRAS used a focal plane designed largely by Frank Lowe of hand-assembled detectors. And it was really a fantastic, fantastic success. About 20 years later came Spitzer, led by Mike Werner and Tom Seufer. Now, Spitzer, an interesting thing happened in these intervening 20 years. The cameras in Herschel at the shorter wavelengths, the near-infrared and mid-infrared cameras, really were commercial products. They weren't built by astronomers. They were something you could buy. And the reason for that is a large commercial investment in building detectors to detect things like airplane engines and rocket plumes and for night vision. So astronomers were able to leverage that large commercial investment into detectors that were adapted for infrared astronomy. But at the longer wavelengths, we didn't have that benefit. And so the submillimeter lagged behind. But Caltech was also leading out here in the submillimeter. Part of the reason the submillimeter lagged is that the atmosphere is pretty unfriendly. Water vapor means that the atmosphere is opaque. And it's even worse than that, because the atmosphere is absorbing. It also means it's glowing. And so when you do astronomy, you're looking through a variable glowing atmosphere and using a glowing telescope. So it's pretty difficult. And so astronomers who do submillimeter astronomy are led to high altitude sites, and this is the summit of Mauna Kea, or aircraft or balloons or rockets, or ultimately space. Now, the Caltech Submillimeter Observatory is just a great place. It's a great place to learn how to do astronomy. It's the only telescope I know where you come in the day and the day crew hands you the keys and says, have fun, call me if you have any problems. And one of the charters of the CSO is, in fact, to field new instruments to further the technical progress of far-infrared astronomy. Over here on the right picture, you can see again the telescope was built once again by Bob Layton, and the director of the CSO, Tom Phillips, is with them. I'd just like to point out they are walking on the mirror. So this is a type of measurement that you can only do at the CSO. Here's Andrew Lang, my thesis advisor. And what in the heck is he doing? Looks like he's fishing, or maybe he's cleaning the mirror. Actually, what he's doing is he's measuring how the detectors are looking out at the telescope. And the way he's doing this is he's got this giant paddle with an absorber. This is called Echozorb, so it's absorbing out in the millimeter wave. And he's taking this paddle and he's switching it back and forth. And you're seeing this signal superimposed on the cold sky, and then moving this around somehow over the telescope to map out the beam. Only at the CSO do they let you do this. This is what a bolometer looked like in the early 90s. Visually, it doesn't look a lot different than the kinds of detectors that Frank Lowe built 30 years before. It's got an absorber. This absorber is actually a flake of diamond. And thermal isolation is really important for making a sensitive bolometer, and it's thermally isolated by fishing wire, very fine nylon threads, so fine you can't really even see them. And it uses a germanium thermometer, basically an improved version of the sensor Frank Lowe developed, shown here, with wires that are so fine you can't even see them. These detectors were built by graduate students under microscopes by hand, using things like tweezers and pointy sticks. You don't want to have coffee the day you have to make a bolometer. Shortly thereafter, we took our ideas about how to make detectors and came to JPL. And JPL has a fantastic resource called the Microdevices Laboratory. And the Microdevices Laboratory has the equipment and the techniques used to make integrated circuits for computer chips, but it's a research laboratory, and you don't use those tools to make computer chips. You use them to make specialized devices that NASA is interested in. So largely these are things that have ultimately a space application. And this is a much, much better way to make bolometers than to do it by sticks. And also the people at the Microlab, and this is Tony Turner and Tony Bonetti, are really, truly excellent. And so in a few years, we made detectors that started to look like this. And this is a micro-machined bolometer. You can see the absorber here is this net-like region, and this is really like a spider web. It's a micro-machined membrane. It's freestanding, hanging out there in the breeze. And so this absorber is this net-like region. It has a thin layer of metal to absorb millimeter wave radiation. And the spider, the thermometer, is this little device at the center. It's a piece of germanium, and actually that part was still hand-assembled. Very reluctant to part with this wonderful germanium. And then the thermal isolation is made by these long, thin, spidery legs. And the sensor is read out by electrical leads. So this is a huge improvement. In fact, the history of bolometer development has been pretty remarkable. What I'm showing here is a progression of sensitivities of detectors going back to that device I showed you in 1946 into the present day. And what I've got here plotted on the left axis is the sensitivity of these detectors. But I can turn that into something that makes more intuitive sense, which is how long it takes using one of these detectors to make a measurement to a certain accuracy. So what I plotted on the right is the time, relative time to make a measurement. And so if we had Dr. Andrews' detector and we're very, very patient, let's say willing to make a measurement that took the age of the universe, 15 billion years, we could make that same measurement today with a high sensitivity detector in just a fraction of a second. So it's really been a breathtaking advance. Now, that only works to a certain limit, and with astronomy, that limit is the level of light that the detector is exposed to. And that level of light has a noise, a random arrival of photons associated with it. So in the case of Herschel, this red line shows that limit. And what that means is there's no point building a detector that's a lot more sensitive to that limit because you're going to be limited by the environment that the detector's in. And the other thing you can see in this plot is this point from Herschel was locked in 9 years before the launch of Herschel. So satellites have a long time scale. They have to pick their detectors well in advance. Now, unfortunately, with Herschel, there's a limit. You can't build more sensitive detectors, and the way to get more sensitivity is to build more of them. And so that became the game in about the 1990s. For the first 50 years or so, people just built better and better detectors. After 1990, it became important to build more of them. And this progression is also impressive. It isn't quite as giddy as the progression in time with detectors, the sensitivity. You can see here with a single detector, a measurement that would take about 10 years would be reduced to 10 hours today. And I think we'd all take that improvement. Herschel has about 325 detectors, so it was about there on this graph. Okay, this is one of the arrays that were developed for Herschel. Each of these devices is a spiderweb absorber and a bolometer. You see all the individual thermometers, and they're read out one at a time. And as soon as we had this detector, first thing we wanted to do was go take it out to an instrument and do some science with it, get some experience with how the detectors work. And of course, this shows how they're packaged. The detectors are actually in this structure shown here. The detectors themselves operate at a temperature of just 0.3 of a degree above absolute zero. And this structure is about the size of a baseball. It's a very compact, busy structure. And in order to have the detectors cold, the detectors are isolated off of these strings. They're Kevlar, basically kite string, so that the detectors can sit at 0.3 degrees, while the outside of the structure sits at a relatively toasty 1.7 degrees. And the first thing we did when we had arrays like this is we wanted to go out and use them. So here we are back at the CSO, and in fact, we're doing the same thing Andrew's doing. We're measuring the beams. Note the great advance in Echozorb paddle technology. We're now mapping the beams out here on the secondary. So there was an array camera called Bolocam that was pioneered this technology. And then we built a prototype instrument for a balloon. And this is a clip for a movie about this balloon venture.
I think it looks really good. We didn't get rained on. We didn't have, let me see,
Hail,
several storms come
fog.
through. We didn't have hail or fog. I can't think of anything that really went wrong so far. There it goes. Here's the release.
She's doing good. She's doing good. You have this instrumentation you've taken care for, and designed for years, and now all of a sudden it's just hanging from a string, and it's out of control.
Okay, Joe, you can just start easing out just a little bit, just to make sure we can move, okay? You doing good?
Yeah, this whole thing is going to get flown on a balloon. It's going to fly from Sweden to northern Canada.
What we're trying to do is really revolutionary. With this telescope, we want to find out how stars were formed, how galaxies were formed.
Now hold it right there, just keep going with a little speed. A little more speed, Joe.
This recovery is going to be far more difficult than I had anticipated. We have a polar bear spotter.
Oh yeah, definitely. Get a polar bear, 1-2 shots, it'll take it down.
A little more right. Walk it, walk it.
I've been out of town this year for about 165 days. Hey, Thomas, you there?
Okay, get ready to stop. Okay, Wood. Okay. Back up, back up, back up.
Wrong way, wrong way. Door. We gotta fly.
Back up.
Oh, they're stuck.
Let it go.
Release it.
Go forward, go forward. Stop.
You're fucking kidding me.
Stop. Go forward, go forward, go forward, go forward, go forward. Keep coming, keep coming, keep coming.
Okay, well, if the launch was hair-raising, the landing was worse. This is a bad landing. Actually, I should say the flight of the balloon was nearly perfect. Okay, and then at the end of its flight, we're out here in Antarctica. Antarctica provides a unique combination of wind and low friction. The parachute has not separated from the gondola here, and this several-ton gondola is being dragged at about 15 miles an hour by the winds. And you wouldn't want to get in front of that gondola to try and stop it. It got dragged like this for over 100 miles. And as it was getting dragged, parts of the experiment started to come off. The telescope and the receiver and the electronics, so forth. And what eventually stopped it was a crevasse. This part of the experiment was never recovered. And there were a few panicked days where the data drives, because all the data is recorded on the gondola, there's limited telemetry in Antarctica. All the data is on the hard drives, which were in a vacuum vessel about this big that was painted white. And but fortunately, the data drives had the good sense to jump off the gondola about 2 miles before it went into the crevasse. And in spite of all the excitement here about ballooning and the challenges involved, what we learned is the instrument worked great. The data were just really fantastic and gave us a lot of confidence that going into Herschel that we knew what we were doing. Okay, so on to Herschel. This is a picture of the Herschel spacecraft, and of course, you see this beautiful mirror. This is the largest mirror for astronomy. It's a 3.5-meter telescope. And then hidden behind this mirror is a cryostat. This is basically a thermos that contains over 2,000 liters of liquid helium. And that liquid helium is used to cool down the instruments. But it's not, in fact, so the liquid helium sits at a temperature of about 2 Kelvin, but that's not cold enough for the detectors. And so there's some additional detectors, which were pioneered on that rocket experiment I mentioned, that cool the detectors down to just 0.3 degrees above absolute zero. Okay, so this is This is what the spacecraft looks like. There's actually 3 instruments tucked away inside this cryostat that are the 3 prime science instruments for Herschel. There's an instrument called SPIRE, which is led by the UK, which has NASA technology contributions, the bolometers I was talking about. A spectrometer, a very high resolution spectrometer called HiFi. I'm not going to mention it too much, but JPL and the Micro Devices Lab also played a big role there in the detectors and amplifiers used in HiFi. And then a 3rd instrument called PAX, which was developed in Germany. This is a small fraction of the SPIRE team, and teams seem to get overlooked, I think, in science and in society. So I'd just like to say, go team. SPIRE was really a great international collaboration. The instrument was led out of the UK by Matt Griffin here in Cardiff in Wales. And the instrument was actually built at the Rutherford Appleton Laboratory just south of Oxford. And with major hardware contributions coming from the UK, the US, France, Italy, and Canada. And what you see here is team night out at the Oxford Dog Track. Turns out you can sponsor dog races for very little money, so we did a lot of going out and congratulating the winning dog. I now have a brief movie about the assembly of Herschel. This will go by very quickly. Spacecraft's launched on an Ariane 5 out of French Guiana. Out its observations away from the Earth at a place called the second Lagrange point. And that's about 1.5 million kilometers away from the Earth, about 4 times the distance to the moon. And that gets the cryogenic system away from the Earth and improves its lifetime. Because when those 2,000 odd liters of liquid helium eventually evaporate, that concludes the mission. So here's some early results from Herschel. And this is a map of the galactic plane. This is actually a region of star formation in the plane of our galaxy. And all this stuff you're seeing here is interstellar dust. Of course, this is a false color image because you can't see out in the far infrared, but it's constructed with 3 color bands here. And the color stretch is suggestive of the temperature of the dust. So the blue regions and white regions are hot dust, and the darker red regions are colder dust. In fact, this map was made in only a few hours, and it's large. It's many square degrees in 5 bands. And I can superimpose upon this map the 2 shortest wavelength bands made with PAX. And these are sensitive to hotter dust. And you can see these regions here of embedded star formation that are heating up the dust. And then using the 3 longer wavelengths of SPIRE, we're sensitive to the very cold dust. And you can see that the morphology of the cold dust actually looks different from that of the warm dust. While the warm dust was kind of more extended, here you see these very filamentary, compact structures. And some of this dust is actually getting pretty darn cold, down to temperatures of 10 Kelvin or 8 Kelvin. And one wonders if these collapsing structures are the first signs of seeding star formation for new stars that haven't been born. This is another beautiful picture of a star-forming region in the Rosette Nebula. What you can't see is off to the right of this picture is a cluster of hot young stars. And these hot young stars are influencing what's going on in this nebula of interstellar dust and gas. And once again, you see the incredible variation in dust temperatures and morphologies, some kind of diffuse hot dust and then some clumpy, cold filamentary dust. These bright regions are regions of massive star formation. So we think that the stars forming in this region will wind up being about the mass of 10 suns. And then you can maybe pick out here these small little dots. Those are low mass star formation, probably with a mass of about the mass of our sun. And then behind this cloud, there's some really cold dust with some stars coming out and colder dust over here. And once again, this dust temperature is getting down around 10 degrees Kelvin and maybe is showing an onset of collapse to form new stars. Half of the capability on Herschel is imaging and the other half is spectroscopy. And I just have this one slide about HiFi, but HiFi is really just an amazingly capable spectrometer. And this is a small chunk of the full spectral coverage of HiFi, and the spectrum was obtained in the Orion Nebula, which is a rich star-forming region. And well, you know, I'm just blown away by the chemical complexity that's going on here. I don't know if anyone knows what all these lines are. The strongest lines you see here, very satisfyingly, are in fact water. And Herschel's finding water everywhere in many environments. And it is indeed an important coolant and constituent in the interstellar medium. And then there's just this rich organic chemistry that's going on, producing wonderful compounds like methanol and formaldehyde and dimethyl ether and so on. Now I want to move on to the cosmology, which is the part that I'm most interested in. And as I mentioned, in the far infrared, we see about half the light that's produced by distant galaxies. Detecting those galaxies is really a way of life with SPIRE. In fact, you detect them even if you don't want to detect them. This is an example of a region of our galaxy that's mapping kind of this diffuse, wispy cloud structure. It's called the interstellar cirrus clouds. So these are clouds that have low opacity. There's not star formation occurring in them. They're just out there. And so this map was made with SPIRE to map out what this cirrus structure looked like. And if I take this part of the cirrus and zoom in, that's what the cirrus looks like. And if I take a smaller region and zoom that out, you see all these dots. And those dots are distant galaxies. Most of those dots are coming from galaxies that are somewhere between half the age of the current universe to maybe 10% of the age of the current universe. Now, if you want to study these dots, this is a field that was chosen. It's actually called the Hubble Deep Field. Now, this region was chosen to be nothing special in terms of seeing the extragalactic universe, just didn't have a lot of stuff from our galaxy in front of it, and has good coverage with a wide variety of telescopes at multiple wavelengths, including, of course, Hubble. For scale here, I show one of the best surveys taken from the ground, which involve many, many weeks of dedicated telescope time and detected a handful of galaxies. And by comparison, the map made by Herschel. And so this image is just jam-packed with galaxies. All of these galaxies are basically coming to us from the early or middle-aged universe. And the variation you see here in the colors of the galaxies are telling you something about their activity, their temperature, and their distance. So this is incredibly rich. One of the things we're learning about far infrared galaxies is you can ask the question, how active were galaxies back then when we're seeing these galaxies? And the answer is that when the universe was about half of its present age, the typical galaxy shown here was much more active than galaxies are today. In fact, the average rate of formation of stars at that time is about 10 times what it is today. And that rate continues to be high as far back as we can see. Now, we're kind of running out of steam when you get out to maybe 10% of the age of the universe with Herschel, but that rate of star formation is still higher than it is today. So it's an interesting question of why the star formation was so much more vigorous back then and what has basically started to turn it off today. Another interesting thing is that how luminous are these individual galaxies? It turns out that many of these guys are very, very luminous. They have luminosities of 1 trillion to 10 trillion suns coming out in the far infrared. And while such galaxies are known in our local universe, they're not nearly as common. IRAS detected just a handful. Something is making these very luminous galaxies much more abundant in the early universe. Another puzzle that nature's given us is that, okay, now this is a much larger field. It turns out Spire is very capable of mapping large regions of sky, so this is now about 12 square degrees. And some of these galaxies in this map, oh, and you can also see some cirrus up here. By the way, that's cirrus. Some of the galaxies in this image seem kind of puzzlingly bright. I mean, they could be very intrinsically luminous, but they seem kind of a bit too luminous. So after we had this image, a campaign was made of studying each of these 5 galaxies in detail from the ground. And so we zoomed in for a closer look in the optical and in the submillimeter. And what we found was that each of these galaxies showed a structure with a high resolution submillimeter image where the image of the galaxy actually broke into several components. And sitting square in the middle of those components was an optical galaxy. And so what's going on here is the optical galaxy that we're seeing is in the foreground. It's in front of us between this distant galaxy. And it has the effect of acting like a lens, except it's a gravitational lens. And so the light from this distant galaxy is getting lensed and amplified by this foreground galaxy. And that lensing effect makes a weird pattern that you see here because of the multiple images from the lens. So all 5 of those were, in fact, lenses, and all these distant galaxies are actually well back in the early universe, 10-20% of the age of the current universe. Now we're basically 5 for 5 in this image, and this is just a small fraction of the total data that's being taken by Herschel. If this rate of discovery continues, in the final Herschel surveys, we're going to have something like 500 or 1,000 of such lens galaxies. Now, I have to say, we're not entirely sure what to do with them. But each one of these guys is a high-resolution picture for studying a distant galaxy in detail. So I think it's going to be very interesting. Another question, if you're a theorist, is you can ask, how do far-infrared galaxies, how does galaxy formation relate to the structure of dark matter? Okay, so dark matter, we think that most of the gravitationally interacting matter in our universe isn't made up of the stuff that we're made of, baryons, but is made out of some weakly interacting type of matter. And with the hubris of the theorist, one can calculate how this matter behaves, because it's just gravitation. Okay, so this is a simulation of taking a bunch of dark matter particles and calculating how their structure evolves with time. Okay, it's just gravitation, but it's a nonlinear process. So it takes a big computer to make these calculations. And so what the dark matter is supposed to be doing is it forms these clumps and this network of kind of wispy filamentary structures. So this shows the projected mass of the dark matter. This is a pretty big region of space. You can see this is the distance to Andromeda, a nearby galaxy. So it's pretty big size. And these dots show the amount of dark matter that are in each of those wells. And the question, okay, so maybe we understand dark matter, I don't know. But the question is how do galaxies relate to this structure? How do you turn on galaxies in these dark matter wells? What can we say about that? So if you remember what this structure looks like, here's an image of, taken by Herschel over a larger area of sky. So this is the Hubble Deep Field that I showed you. And this is really a big area of sky. This is the moon for scale, so it's many square degrees. That's a lensed object, by the way, another one. And I don't know if you can make it out with your eyes here, but what you see is that the distribution of galaxies in this image isn't random. Okay? There's a clustering of galaxies. If you take one galaxy, it's much more likely that the next galaxy is going to be close to it. Okay? Galaxies like to clump together. And so this structure that you can see with your eye is actually in good agreement with the structures predicted from dark matter. So that's neat. Another thing that comes out from this image is a question of how much dark matter do you need to have a galaxy form and start to turn on and form stars? And this is not something you can actually see with your eye, but there's a clustering on smaller scales that is related to that process. And the answer turns out that you need a mass of about 300 billion stars in the form of dark matter, which is about a third of the mass of our galaxy, to start one of these new galaxies. Okay, well that's the conclusion of my talk. But I want to say that we're far from done. Herschel's far from done, first of all. It's about halfway through its cryogenic lifetime, and we're just drowning in data, I have to tell you. It's really pouring out, and there's more results and more surprises on the way, I'm sure. But beyond Herschel, while we were worrying about building the detectors for Herschel, another revolution happened in far-infrared detectors, and that's a new generation of detectors that are based on the principles of superconductivity. And this allows for more sensitive detectors for things like future space missions like Spica, and for large arrays of detectors that we'll need for the next Caltech ground-based observatory, which is CCAT. Thank you very much.